Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's get into it. Okay, there we go. All right, so essentially what I want to do today is get through a bunch of probability problems with you guys, just a variety, kind of putting to use the things that we've gone over. They're from the probability example set 2, which you can find on your on the class webpage. So we're just going to go through a bunch of examples. That's basically it. This one we've already done. I think 2 of them we've already done. Last time we learned a very, very important formula and we put it to good use. This was Bayes' rule, Bayes' theorem. And we used that. Use that to solve this. Where was it? So I know we solved problem 3 at some point. And there, here. But yeah. So this is what was covered last time after the announcements. We did the very famous disease example. What is the probability of you having a deadly disease if you know the prevalence of the disease in the population and you take a test where you know how effective it is. And we got some surprising results, but those were the true results. And we kind of even looked at it by the numbers and just saw how it was. And we did the coins example. So that was problem 3 from handout 2. We used
I think this was for the other class.
This was for both classes.
I don't think we went over this yet.
Yeah, so remember our class was canceled. And so I told you guys to watch the video of the other class.
I looked up the video and it wasn't there. It said the last update was like 6 days ago.
Oh, that's strange. I thought I uploaded it. Geez, I'm gonna have to check that later. Thought I uploaded that. So I don't know, should we? So problem 1, I did not go, you didn't see the solution to problem 1 then either. Is that what you're saying?
Yeah.
Okay. I wasn't planning on doing that, but maybe I'll also go through that quickly then. I was pretty much planning on going through most of these rapid fire. I don't know if I can just go through this one as well. So maybe we can just redo it. So we have a rare and deadly disease. 1 in 10,000 people have the disease. And you're a hypochondriac, you believe you have the disease. And so you go and you get tested for the disease and the result comes back positive. So you're freaking out because it's a deadly disease. And you're just like, you're freaking out, right? So the doctor tries to calm you down. He says, well, you know, the test does give false positives, like 1% of the time. And, it's like, I mean, it's 99% effective if you have the disease that it'll tell you, but it does give false positives like 1% of the time. You're probably in that 1%, right? So that's how the doctor is trying to calm you down. And you're like, yeah, you leave the doctor's office, you go home, you try to look over your will, you try to get your affairs in order, tell everyone you love them, all that stuff, because you're like, oh, there's a 99% chance I have the disease, right? Because it says so right there. It's a 99% chance that if you have the disease, the test will pick it up. So you're like, yeah, I have a 99% chance of having this thing. It could only be wrong 1% of the time, and yeah, so you think you're pretty much as good as dead. Now, the question is, what are the chances you actually have the disease? Which sounds very suggestive because a lot of people reading this would think, oh, it's 99%. Was it actually? Is it actually? So we went through this and we actually used Bayes' rule to do it. So we set up some sets. Let D be the event a person has the disease. Let POS be the event a person tests positive. Let NEG, although I don't think we even use this, but positive complement be the event person tests negative. Okay. And so now we can actually put in the probabilities. We know that there's a rare and deadly disease. 1 in 10,000 people have it, which means the probability. So this is the information we're given. The probability of having the disease is 1 in 10,000. And of course, this means the probability of not having the disease is 1 minus 1 in 10,000, which is going to be, of course, 0.9999. Right? And what else do we know? Well, we're not told this. This we figured out based on the first thing. I'll put that in blue. What else do we know? We know that the test gives a false positive in 1% of cases. A false positive is when the test says you're positive, but it's wrong, right? So that's a false positive. So basically what that means, that's a conditional probability. That is basically saying that given that you don't have the disease, the test will say positive 1% of the time. So this is a false positive. Okay. We also know that given that you do have the disease, the test will pick it up and show positive 99% of the time. Okay. What else? Okay. I think that's it. And so now you have to realize what you want. We actually want the probability. What is the probability that you have the disease? Well, you are someone who tested positive by this test. So the probability, what we want is that given that you tested positive, what is the probability that you actually have the disease? right? That's what we want to know. And now, when you realize that you want a conditional probability, and you realize also that you know the probability in the conditional in the opposite order, you know, that kind of hints to you Bayes' rule might be useful. So this hints Bayes' rule is useful. Now, by Bayes' rule, the probability of disease given positive is going to be equal to the probability of positive given that you have the disease times the probability of having the disease over the probability that's positive given that you have the disease and probability of having the disease plus the probability that you test positive given that you don't have the disease times the probability of not having the disease. Right, so that was Bayes' rule. Pretty sure that you guys saw that one. I'm using this formula right here. Probability of A given B is probability of B given A times probability of A divided by probability of B given A times probability of A plus probability of B given A complement, probability of B complement. Okay, so that's what I'm using here. Now, of these guys, one thing that we do not know is the probability of positive given. No, we actually know everything, don't we? We know everything that we need for this formula. If anything that we didn't know, we could use like the complement rule and things of that sort. But here we actually know everything. So positive, given that you have the disease, is 99%. Probability of having the disease is 0.001. Probability of testing positive, given that you don't have the disease, is 0.01%. Probability of not having the disease is 0.9999. And did work this out last time. I don't want to waste my time typing that in calculator again. Let's see, do I have the thing where I wrote it out? Yeah, it was actually, oh, we got it here. 0.0098, which is like 0.98%. It turns out you have roughly 1% chance of having this disease under these conditions. Right. Now, 1% probably isn't great odds for you, but it's a far cry from 99%. And this is one of the ways in which I was mentioning earlier, how sometimes your intuition can really lead you astray with probability, but the truth can be very far off from what you are guessing. If you told anyone these statistics here, they'd probably still freak out. Like, the test is 99% effective, it's wrong 1% of the time. So you're telling me that I'm 99% sure to have this disease? No, you're actually less than 1% sure to have the disease. So that's true. And I guess I can show you a little bit why this actually makes sense. Does this make sense? And I spoke about this for a really long time in the last lecture. I better find it. But basically what happens is, if you imagine that there are like 10,000 people. So these, all these little circles are people in your population, right? So this is the population of 10,000 people. Look that in. Right? When you actually start to write things out mathematically and start to look at it, the answer is going to actually be a little bit obvious. Let's say this is the guy who has the disease. Right? So out of 10,000 people, one person on average will have the disease. Right? Now, we're told that you get a false positive in 1% of cases. So let's look at the people who would have gotten the false positive. Let's pretend that they're up here. So you have 1% of 10,000, which of course equals 100, get false positive. So there are 100 people in a group of 10,000 people that the test will say they're positive when they're actually not. So now, when you say, given that you test positive, you need to realize that what actually happens is all of these guys are now removed from the sample space because we have a condition. We know you tested positive. You're not just a part of the random population anymore. You're part of the population that tested positive, which means you're not a 1 in 10,000 chance. So the probabilities before don't really apply to you directly. What does apply to you is the fact that in a list of 101 people, one of whom has the disease, you are one of those people. So there's 101 people, and this is you, potentially. Hopefully you're not the red one. I mean, you could still be, but potentially you are the guy who does not have the disease. And so really your chances, probability that you have the disease, given that you're in the positive group, as in the test told you positive, is really 1 over 101. And that's roughly, I think it was 0.99%, right? So when you actually start to set things out with a diagram or a table or Bayes rule or something that we know logically and mathematically works, you realize that the true answer actually comes out pretty nicely. But yeah, a lot of people actually just jump to conclusions with something like that. However, you're freaking out, so your family tells you, hey, maybe you should get a second opinion. You know, you're not going to like throw your life away because this one doctor. How do you know that they did the test right? So everyone's trying to cheer you up and say, all right, get a second opinion. So you go for a second opinion and you get another positive result. Like you can't catch a break. You test positive again the second time. So now the question is, all right, now what are the chances that you have the disease? Right? So in part B, probability you have the disease given that you test positive a second time. Right? That's what we want. So now what we would do here, there are many ways to do this, but for a two-part problem like this, I would say I think it's the most straightforward way here, but we will update PFD here. For you, PFD is now 0.0098. So you're no longer some random dude off the street where the probability for you having the disease is 1 in 10,000. You are someone who has results. You have test results. You have updated chances. So you have a different chance of having the disease. Now, this means the probability that you don't have the disease is, of course, going to be 1 minus 0.0098, which is going to be 0.9902. And then now, when you go probability, having the disease, given that you test positive, second time, is going to be the probability that you're positive, given that you have the disease, times the probability of having the disease over positive, given that you have the disease, times the probability of having the disease, plus positive, given that you don't have the disease, times probability of not having the disease. So here we end up with positive, given that you had the disease. The test is still tested to be 99% effective. However, the probability that you have the disease is now 0.0098. And this is 0.99 times 0.0098 plus, now this is going to be 1% of the time. It's going to be wrong. And then you have the 0.9902 here. Turns out now, of course, when you test positive 2 times, it's going to be more likely that you have the disease. I mean, come on, like you tested positive twice. What are the chances that both tests were faulty? Both doctors are obviously you went to a different doctor, but it's not 99% still. It's 49, so that's about 49.49%, which is a lot higher, but still, even after a second test of being tested positive, you still, right? And again, what that means is you're now one of the 101 people who went and got positive tested again, so that it becomes a smaller group, and then you're just one person out of that smaller group. It turns out in that smaller group, maybe around 2 people will be tested positive, and so you'd be 1 out of 2, right? You'd have the one person who actually has the disease would probably test positive, and then the 1% false positive result out of 100 people, that would mean that 1 person would test positive even if they don't have the disease. So now you have 2 people who potentially have the disease, and you're probably one of them. You're 1 out of 2, 50%. So yeah. But I did talk about that at length. I gave some other examples last time, but let's not do that right now. And last time also, last time that no one has seen, somehow I forgot to upload the video or didn't do it right. Maybe I uploaded to some random playlist. Did problem 3 next, and that was because problem 3 also used Bayes. I don't think you need the Bayes for any of the other ones. So on a table, there are 5 coins. 2 of them are double-headed. I mentioned that you can't actually create an unfair coin. It's actually mathematically and physically impossible. The only way someone could actually create an unfair coin is to have 2 of the same sides, like Two-Face in Batman. Or they'd literally have to bend the coin some way. And then if it's slightly bent, you can probably change the probability from heads to tails, but it's otherwise it's impossible. So someone's trying to cheat you, and they say, oh, if you get tails, I'll do whatever, but they want to bolster their chances. So they actually put more heads than tails. So you have 2 of the coins that are unfair. They're double-headed. You pick a coin at random, you flip it. What is the probability that you actually get heads? And so here we set up fair coins. So for the fair coins, 3 are fair. 2 are unfair. And just do fair coins. That's just coins. So I'm going to call these guys fair. That's the event, and unfair. So this is the events. The class, I call them F and U. Yeah, couldn't do that. So I just wrote out the words. Yeah, can't do that. So here's what we know. So we know the probability that you'll get heads given that you chose a fair coin. Well, that's just, it's a normal coin, it's a half. However, the probability that you get heads given that you chose an unfair coin, well, that's 1. Whatever side it lands on, you're going to get heads. So now we want the probability of getting heads. So we can do by Bayes version 1. We know that the probability getting heads is, well, the probability that you get heads given that you chose a fair coin times the probability of choosing a fair coin plus the probability that you got heads given that you chose an unfair coin times the probability of choosing an unfair coin. So that's Bayes version 1. Probability of getting heads if you chose a fair coin is a half. The probability of choosing a fair coin, well, there are 5 coins, 3 of which are fair. So this is 3 over 5. Plus the probability of getting heads if you chose an unfair coin is 1. What are the chances of choosing an unfair coin? Well, 2 out of 5. So here we have 3 out of 10 plus 2 out of 5, which I can multiply by 2 over 2. So this is 4 out of 10. So the answer is actually 7 out of 10 that you'll get heads. You're more likely to get heads than not. Significantly so. 70% of the time you do this experiment, pick a coin at random from the table and flip it, you'll get heads. And the above is called finding probabilities by conditioning. So we condition on whether you chose the fair or the unfair coin. We use conditional probabilities to figure out this major probability.
Can I ask a quick question?
Yes.
When I was trying it right at the beginning, I wrote out the 5 coins and then gave the options for those 5 coins. So for the first 2 coins, it was just heads, heads, heads,
Yeah.
heads, heads. And then for the next 3 coins, I wrote heads, tails. So that way I had like 10 options to get. And then 7 out of them were heads, and then 3 of them were tails. So then I got to the answer 7 out of 10. Is that like a sufficient way of getting to that problem, or is it more complicated than that?
That's perfectly fine. What you did was enumerate. What you just described was called enumerating, which means you literally just you specifically counted out every possibility. So you went to you looked at say coin 1, and you looked at coin 1 and you said, okay, that's 1 heads and 1 tail, right? Coin 2, that's another heads and another tail. Coin 3, that's another heads and another tail. So those were the 3 fair. And then coin 4, you said, well, that's a heads and another heads. And then coin 5, well, that's another head and another head. So this here would be your fair coins, and this here would be your unfair. And you'll know that a coin flip is only going to take one of these options. Right? Now, there are 10 total options. And 7 are H, right? So you can pretty much count 1, 2, 3, 4, 5, 6, 7. And so probability of getting heads is 7 out of 10. Yeah, so you can use the basic probability. So that would work. That was a second solution I was going to give, but I ran out of time in the last class, I think. But yeah, you could do that. But of course, that works when you have a small number of things, right? So if I was like, oh, we're playing Dungeons and Dragons and we have a D4 dice, and I'd mix it up, and then you're going to be like, oh, how am I going to count this? It gets harder. You want to. This way is fine. Both either of these ways are fine, right? I wouldn't have a problem with either of these. Okay, let's do the famous birthday problem, which normally when I do this in class, I actually do the experiment and ask people to say what their birthdays are. And so far, we've always had 2 people sharing the same birthday. Because normally when we're not in like online mode, like routinely an 1108 class is more than 23 people. It's usually like 25 to 30, which is a decent number. It's actually more likely that 2 people share the same birthday than not. With the online classes, I have less people. I think in this class, there may be 15, 16, something like that. So I don't know if that probably was good enough. But it turns out if there are 23 people in a room, it's actually very likely that 2 people share the same birthday. Well, I wouldn't say very likely. It's more likely than not. There's more than a 50% chance that that occurs. Yeah, it actually goes up very rapidly. Of course, by the time you get like 366 people in a room, then yeah, the probability is 100% that 2 people share the same birthday. But it turns out that you have a more than likely chance as early as 23. Yeah. So let's actually see how that is true. Like this was one of the probability teasers that I just told you the answer. Now we're going to actually show it. So how can we do this? Okay, so we're going to assume a year has 365 days just to make it easy. Forget about leap years. So people who were born on February 29th, sorry. Yeah, what is the probability at least 2 people share the same birthday in a room of 23 people? There are a couple ways you could do this. So one, what I would say is because we can allow repeats, we can think of the people as a set of tuples of birthdays, 23 tuples to be precise. So we can say our sample space is just a set of all tuples, say x1, x2, x3, going all the way down to x 23, such that the xi are birthdays. Right? Because a repeat could happen, I don't want to think of it as a set of people. I probably think of them as a bunch of tuples. but we have every possible combination of birthdays happening. We actually know a counting principle to deal with that. Whenever you have a tuple of size r and there are n options in each, the probability is n to the r. In the same way, there are 365 things that each of these x's could be, and there are 23 options. So by the multiplication rule, this is 365 to the 23 possibilities, which is a huge number, right? You wouldn't want to list that out, right? So we have that. Now, we want probability that at least 2 have the same birthday. And I don't want to write that out all the time. So call that B, right? It's the event that they have the same birthday. At least 2 have the same birthday. Now, when you look at that directly, that is like you don't want to actually do that, because now you're going to say, well, it could be the first and the second person, or the second and the 17th person, or the 23rd and the 15th person. There's so many combinations. Like, you don't want to have to do that directly. So what we can use here is this is equal to 1 minus the probability of B complement. So you could have 2 people or 3 people or 4 people. So the thing that I just described happening with 2 people, you could also do it with 3s and then 4s and then 5s and then 6, all the way up to 23. Like, you don't have time for that. Ain't nobody have time for that, right? So what you can realize, though, is that the opposite of at least 2 is 0. Well, it would be 1, but that means that not 2 people share the same birthday. If only 1 person has this birthday at most, that means not 2. So this actually means, so this is the 1 minus the probability that no one shares the same birthday. Right? If you can't find 2 people that share the same birthday, it means no one shared the same birthday. And that is actually a little bit easier to manage. Basically, what you're saying now is that this means the tuple in S will have different dates, i.e., no repeats. And we actually know how to count that. The number of tuples of a certain size that has no repeats in any of the options. So that is the size of B complement equals number of tuples in S that do not repeat dates. We actually know how to count that. That is actually a permutation. So this is just P of 23 well, we're choosing from 365 people, and then we just want to make sure, yeah, we're choosing 23 options from 365. But we want to choose 23 different options and line them up in an order, line them up in tuples. So this means the probability of B complement is equal to P of 365, choose 23, over 365 to the 23. And when you kind of write this out, what you'll realize is happening is that what you're doing is you're multiplying a bunch of probabilities where the denominator is 365. So the first person can choose 365 out of 365 days to have his birthday, but then the second person can only choose 364 because he's not allowed to pick the day that the previous guy took. Messed up again. Then the next guy can only choose 363 days because he's not allowed to pick it up. And this will go down 23 times, right? This will go down to 365 minus 23 plus 1, right? So 365 minus 23 plus 1. And that we know is a permutation. And it turns out this is roughly 0.0 0.44927. That's probably of not having the same birthday, which means the probability of having the same birthday is 1 minus 0.4927. So that's 0.5073. So that's roughly a 50.73% chance. Once you have 23 people in a room, it's actually more likely than not that you share a birthday with somebody. And yeah, surprisingly, actually true. Like if you watch some of the old videos, I actually do this experiment in the class where I actually literally go through the class and have everyone say their birthday. We always find someone in all the classes. Although I think I only recorded and posted like 2 of these classes so far.
Are we gonna do it?
Well, I mean, it's a small number of people. We can if you want, but I wouldn't expect anything from it.
Why not?
Like I wouldn't bet on it. Yeah, maybe you guys can like type your birthday in the chat or something,
Yeah.
and then we'll see if there are any repeats. Or anyone can just shout if they already see their birthday being typed. They're like, wait, that's mine. May 20th, September 18th, May 24th, September 13th, January 7th, October 22nd, February 18th. I don't think there are any repeats yet. And I'm not even sure if everyone did it. 1, 2, 3, 4, 5, 6, 7, 8. Well, not everyone has typed. I don't know where everyone is. No repeats yet. But I wouldn't bet on it though. Like in a class of more than 23 people, I'd actually bet on it. If that. Once upon a time, I was in a probability class where the instructor like bought a lotto ticket. He's like, he did the birthday problem. It was like, if I'm wrong, I'll give you guys the lotto ticket. And then, yeah. Yeah, certain things you can bet on. Oh, there's another way we could do this. Yeah, a little bit more than half the class responded. I don't think there was a repeat yet. Another way. If you didn't want to do the permutations, you could do it a different way. So for example, probability, but again, I would go through the complement. Probability that 2 people do not share a birthday, right? So that would be that would be equal to, well, the first person can pick any day out of 365, but then the second person has to pick another day, right? So he has to pick 364 out of 365. So that's just the probability that if I pick any two random people, that the probability that those two people don't have the same birthday is going to be 364 over 365, right? So now, suppose this happens for every pair of people. Okay, suppose every two people you pick, this is the truth, which means that no two people would share the same birthday. So now all that matters is you would count the number of pairs, like how many times would this actually occur? So the number of pairs, well, that you can think of as a combination. That's going to be 23 choose 2, right? Out of 23 people, choose 2 people to compare. So that's the number of pairs that you can have. So now by independence, probability no two people no pair has the same birthday. Well, that just means the first pair doesn't, the second pair doesn't, the third pair doesn't, and you multiply them. So that'll be 364 over 365 times 364 over 365. So it means the first pair and the second pair and the third pair and the fourth pair. We know because of independence, you can multiply the probabilities, and you will have 23 choose 2 such pairs. And so essentially this becomes 364 over 365 to the 23 choose 2. And so this means the probability of B, at least 2 people share the same birthday, is going to be 1 minus that. And that is going to be roughly 0.5073. You get the same answer. In part B, it's very similar to the solutions in part A. It's just that your birthday is now, you are one of the people, which means that one birthday is now off the table. You just want to check everyone against your birthday, right? So if you're in the group of 23, what is the probability that one of these other 22 people share your same birthday? It's exactly the same reasoning, except instead of 23, you would use 22. And of course, instead of 365, you'd use 364 because you have removed yourself and your birthday from the group, and now you're judging the other 22 people. So here we can remove you and your birthday from the group and compare the other 22 people to you. To not share your birthday, they must each have one of 364 options for dates. So this implies, by the first method I mentioned, the probability no one shares your birthday is going to be 1 minus 364 to the 22, P of 364, choose 22. And that was 47.66%. So that's method 1 way of doing it. And method 2 would be similar. 1 minus 363 out of 364 to the 22, choose 2, and you'll get the same thing. Okay, so that didn't work out. Try these for next time. So the plan was to finish up to like problem 6, and then we could start problem 7 next class, because it leads into another topic that I want to show you guys. But I guess we'll just do all of that next time. Okay. And again, you can find the handout on the class webpage, but we're already out of time, so I'm going to let you guys go. We're actually over time. So that's it. Enjoy your weekend. I will be sending out like a schedule or a doodle poll because I actually want all groups to like meet with me and go through their project. I'm already meeting with a group today, I think from this class. So I'll send you the Zoom link in a little bit. But otherwise, I have my office hours full today. So I'll just send you some options for over the weekend up to early next week, so you guys can meet with me to see where you guys are doing with the project. Other than that, I will see you over the weekend. So just look out for that email.